Good morning, dear students. In today's class, we are going to see dispersion in optical fiber. So, before starting to dispersion, just recall how many types of losses we have studied in the optical fiber here. So, we have studied almost three losses which affects the signal while transmitting in the fiber optic cable. The first loss which we have seen was the absorption loss. So the absorption loss was the imperfection due to atomic structure of the fiber material. So here the absorption can be intrinsic or an extrinsic, right? So in intrinsic, we have seen that transition of electrons from lower energy to the higher energy state. So due to which there is a loss of signal in the optical fiber. So again an intrinsic in which the water molecules gets affected in the signal. So after that we have seen scattering losses. In scattering losses we have seen Rayleigh and Mie scattering, and the light gets scattered when the operating wavelength is less than or greater than the optical wavelength. And we have seen the bending losses also. In that we have seen macro bending and the micro bending. So that occurs due to manufacturing. Here the micro bending and macro bending are occurs due to manufacturing losses. So how we can overcome these losses means while we have to make a new optical fiber. So here the dispersion is a little bit different as compared to the absorption, scattering and the bending losses. So now we can see the dispersion. Now let us understand what is meant by dispersion. Uh, this is the optical cable. This is the core. Here we have the signal is traveling towards the core. This is the core, and inside which light is going to transmit, and this is the cladding here. So when the light pulse, we are going to send that to as 1 0 here. This is the input pulse, right? So 1 0 1 0, that is on off to the LED or a laser ascent source here. So we are going to transmit the signal over a period of time. That is when the signal is being transmitted inside the optical cable here, right? So there is an overlapping of, here it is, if from the output side we can see some overlapping, right? So there is an overlapping of two signals. Here we are giving the input as 1 0 1 0. So here in the output side there is a overlapping of two signals. So that is, we have seen the signal as, right, 1 0 1 0. So inside this is due to there. So why this overlapping occurs means, inside this it is due to the refractive index of the core, there is an overlapping of the signal. So when the output is received at the receiver side, right here, the overlapping of pulses take place. So we can't distinguish between the ones and zeros. So such cases are also known as interference ISI, that is inter-symbol interference. So here it will not be able to receive the signal properly at the receiver side. So in short, we can say that when the optical signal or pulse guided into the fiber optic cable or a link, right? So here we are giving the input pulse here. So it is guided into the fiber optics. The pulse gets spread here, right? Is in output side it was spreading. Though the pulse gets spread and broadened as transmitted through the fiber here. So such type of occurrence is called as a dispersion. So what is the effect of dispersion means? The spreading of an optical pulse limits the information carrying capacity of the fiber. That means your fiber optics will not transmit as the data is to be transmitted. So here we are going to see how we are going to overcome this dispersion losses. There are two types of dispersion in an optical fiber. That is, the first one is intramodal dispersion and intermodal dispersion. So intramodal is also known as chromatic dispersion, which occurs in all types of fiber. That means it occurs in single mode as well as in multimode fibers. And in intermodal dispersion occurs only in multimode. It does not take place in the single mode because it only transmits their fundamental mode. So now in detail we are going to study about the intermodal and the intramodal dispersion. So intramodal dispersion is nothing but it primarily depends upon the fiber material. So the fiber materials used for the manufacturing of silica and OH bond like SiO2 etc. Okay. So in that depending on the fiber material there are two types of intramodal dispersion. One is material dispersion and another one is waveguide dispersion. Now we will see in detail what do you mean by material dispersion. So the material dispersion takes place due to different wavelengths traveling at different speed inside the fiber. So once again, here the material dispersion takes place due to different wavelengths traveling at different speed in the inside the fiber. So it depends on the velocity of light traveling inside the core. So as we know in the step index fiber and the gradient index fiber, the refractive index is going to be changed in gradient index. So the different wavelength will be traveling at different speed inside the fiber. Now we'll see that material dispersion, how we are going to minimize this material dispersion. So we can minimize by using the wavelength such as 850 nanometer or 1300 nanometer and 1550 nanometer wavelength, which is also known as zero dispersion wavelength, and it is denoted as ZDW. So if we calculate the dispersion losses due to dispersion, the loss will be minimum, almost it is zero at almost it will be zero at 870 or 3300 and 1550 nanometer. But every time we can't send the data through the light in which the wavelength is 870 or 1300 because the attenuation losses due to absorption and the scattering is more at this wavelength. That's why we have shifted that, and it is also known as dispersion shifted fibers, and it will be at 1550 nanometer. So here the dispersion losses are zero. That means the broadening of pulses will be less at that time, and the attenuation due to other effects also will be very less. So when the wavelength is less than zero dispersion wavelength, that is ZDW, it travels slower, and when it is higher than ZDW, it travels faster. So thus the speed is changed and it is used in such a way that all the waves passing through the fiber will move with a constant speed, and hence the material dispersion is minimum. And this dispersion will not occur in the single mode fiber and will happen only in the multi-mode fiber, right? So as we said, this material dispersion will occur in a single mode fiber. So let us see the material dispersion model. Here the pulse spread due to material dispersion may be obtained by group velocity, that is represented as tau g. Therefore, the transient time or group delay at tau g for a light pulse propagating along a unit length of a fiber is the inverse of a group velocity Vg, right? So we know the formula for tau g. We have seen these values in this cylindrical fiber. That is the value of tau g is equal to 1 by Vg. Since we know the value of Vg is equal to d omega by beta, d beta. So here the value is 1 by Vg, right? So by taking reciprocal, we will get the value as d beta divided by d omega. So take this as equation number 1. So from the electromagnetic propagation, we know the value of Vg, right? So we know the value, we have derived the value of group velocity. So the value will be Vg is equal to C divided by n1 minus of lambda dn1 divided by d lambda, right? Take this as equation number 2. Now substitute equation 2 in 1, we will get, so we know the value of 1, right? So the equation 1 is nothing but tau g is equal to d beta divided by d omega. So we have find out the value of d omega divided by d beta. So by substituting this value, we will get the value of tau g is equal to 1 by c into n1 minus of lambda into dn1 divided by d lambda. Take this as equation number 3, where here we have the value of n1, right? So this n1 is the refractive index of the core material. Next, the pulse delay, it can be represented as tau m, right? So here the value is tau m. Due to material dispersion in a fiber of length is given as tau m is equal to, right? So here the length is, we are taking as length L, right? So we are representing, for instead of 1, we are representing L. So L by C into n1 minus of lambda d n1 divided by d lambda. So the RMS pulse broadening due to material dispersion sigma m may be obtained by using Taylor series expansion. So the Taylor series expansion for this material dispersed sigma m is given as sigma m is equal to sigma lambda d tau m divided by d lambda plus sigma lambda into 2 d square tau m divided by d lambda square plus etc. So take this equation number 5. So as the first term, what is the first term? Sigma lambda into d sigma m divided by d lambda. So as the first term usually dominates, especially for the source operating over 0.8 to 0.9 micrometer wavelength range. Therefore, we can write the value of sigma m is equal to sigma lambda into d tau m divided by d lambda. Take this as equation number 6. So pulse broadening or spread may be evaluated. Pulse broadening or pulse spread may be evaluated by considering the dependence of tau m and lambda. Therefore, equation 4. So this is equation 4, right? So by taking a differentiation of this value, we will get as d tau m divided by d lambda is equal to, like, L by C constant, and we have to differentiate this with respect to lambda. So it will get dn1 divided by d lambda minus of lambda. So we have to differentiate this as UV method. So we will get lambda into d square n1 divided by lambda square minus of dn1. So the value of lambda will be equal to 1 and dn1 divided by d lambda. So here you will be getting the value like this. So plus dn1 divided by d lambda minus dn1 divided by d lambda get cancelled. So by rearranging this expression, we will get d tau m divided by d lambda is equal to, here we have the negative sign, right? So minus L lambda divided by C into d square n1 divided by d lambda square. Take this equation number 7. Now substitute this equation 7 in 6. So here we have the value d tau m divided by d lambda. So we have to substitute for this d tau m divided d lambda is equal to minus L lambda divided by C into d square n1 divided by d lambda square. So the value of sigma m will be equal to sigma lambda into minus of, so by taking the modulus value, actually the value will be equal to minus sigma lambda into L lambda divided by C into d square n1 divided by lambda square. So the spectral spread will be in positive, or we are taking the modulus value, we will get sigma lambda L by C into lambda modulus of lambda into d square n1 divided by d lambda square. Take this as equation number 8. So the material dispersion parameter can be represented as m, so which is defined as m is equal to 1 by L into d tau m divided by d lambda. So by substituting the value of d tau m, so we know the value of d tau m divided by d lambda is equal to lambda L by C into modulus of d square n1 divided by d lambda square. So from this the value of L get cancelled. So we will get lambda by C into d square n1 divided by d lambda square. So here we have the value m, right? This m is expressed in unit of picosecond per nanometer per kilometer, right? So now we will see the waveguide dispersion. The waveguide dispersion is caused due to the difference in index of the refraction between this core and this cladding, right? So it occurs because a single mode fiber confines only about 80% of the optical power to the core, right? So here the 80% of the optical power will be confined in the core. So the dispersion thus arises, and since 20% of light propagating in the cladding travels faster than that of confined to the core, right? So here 20%, 80% will be traveling towards core, and the remaining 20% will be traveling towards this cladding in a faster manner. So the amount of waveguide depends upon the fiber design. So this dispersion will be depends upon the design of the fiber. So the index of the refraction means at which the angle is to be refracted. So whenever you are going to incident the light, that is a different wavelength. Here we have lambda 1 and lambda 2, so on. It has been inserted at the acceptance cone, right? And it is going to be incident at pi 1. Here we have pi 1 and pi incident at pi 2. So there is a difference in the index of the refraction between core and cladding, which results in the track effect between the core and cladding portion of the power. So such type of dispersion are also known as waveguide dispersion. Now we can see intermodal dispersion. So intermodal dispersion occurs only in multimode fiber. When more than one mode is transmitting through the fiber, they will have different wavelength and have to take different time to propagate through the fiber, right? So this leads to an intermodal dispersion. So here we have lambda 1 and lambda 2, which will be received at the different speed, right? So it will be received at the different speed at different time at the receiver side. Then each mode will have different wavelength with a different speed, and hence they reach at the end of the fiber with a different time. So this results in pulse broadening. So this can be distorted first. So such a phenomena is called as intermodal dispersion. As we have seen, due to spreading of light or broadening of light in the optical fiber, there is a information carrying capacity becomes very less, right? So if you want to calculate how much is the usable bandwidth, this is one example I have shown, right? So it can be calculated based on the bandwidth distance product. It can be calculated based on the bandwidth distance product, and this value is expressed in hertz kilometer. So let us see the example. If a fiber is having a bandwidth distance product of 250 megahertz kilometer and the length of the link is 5 kilometer, then what is the usable bandwidth over the link? So to find out the usable bandwidth, the formula is ratio of bandwidth distance product to the length of the link or distance of the link. So here in question it is given as bandwidth product distance product is 250 megahertz, right? Megahertz kilometer. So here the usable bandwidth is equal to 250 megahertz kilometer divided by 5 kilometers. So 5 kilometer get cancelled. So by simplifying this expression, we will get 50 megahertz. So this is the usable bandwidth of an information carrying capacity of an fiber optics. Thank you, students.